Ever wondered how your phone can unlock just by looking at your face? Or how a computer can recognize a face even if you're having a super bad hair day, or when you have bags under your eyes, or even when you start wearing glasses? Behind the scenes, a powerful concept is often at play: principal component analysis, or PCA for short. PCA is a statistical procedure that allows you to summarize the information content in large data tables by means of a smaller set of summary indices that can be easily visualized and analyzed. That was a mouthful to say and hard to understand, so instead of deciphering that definition, let's explain PCA by doing something fun. Let's turn faces into math. Let's start by examining a simple grayscale image of the GOAT instructor Harish Prakash. A typical grayscale image like this one is essentially a 2D grid of pixel intensity values. Hypothetically, let's say this image is created using a 100 by 100 pixels. You have 100 rows and 100 columns, therefore equaling 10,000 pixels in total. Each pixel has a value between 0 and 255 indicating the brightness, 0 being black and 255 being white. So a face image is just a matrix of 10,000 numbers representing pixel brightnesses. That's 10,000 numbers to describe one face. And if we have hundreds of these faces, well, that's a lot of numbers. But here's the thing: not every pixel is equally important. Can we somehow compress this data without losing what makes a face a face? That's where PCA comes into play. PCA is a tool that looks for patterns. Specifically, it searches for directions in this high dimensional space where the data varies the most. Imagine this: every face in your dataset, even though it's just an image, is really a point in a 10,000 dimensional space. That's hard to picture, so let's simplify. Suppose your faces in a dataset only had two features, maybe brightness of the left eye and brightness of the right eye. You could plot each face as a dot on a 2D graph. If all the dots lie roughly along a diagonal, that tells you something. Those two features are correlated. When one goes up, the other one does too. In this case, PCA would say, let's rotate our view to align with that diagonal, the direction of maximum variance. In higher dimensions, it's the same idea. PCA finds new axes, new directions that better capture the structure of the data. These are called the principal components. And here's the key insight: even though the original space had 10,000 dimensions, most of the interesting stuff, the patterns, the variability, often lies in just a few of them. So if we rotate and reframe our data to lie along those directions, we can compress it without losing much information.
Let's dive just a bit deeper into what PCA is actually doing under the hood. First, think of each face as a vector, a point in a very high dimensional space. If each face has 10,000 pixels, then each face is a vector in R10,000. That's a 10,000 dimensional vector space. When we stack all of our face vectors into a big matrix, we essentially create a dataset of shape n by p, where n is the number of face images and p is the number of features, in our case, pixels. We can separate the data into columns with vectors x1, x2, and so on. We also have another variable, which is the loadings, which we will multiply to the vectors. The first step PCA takes is to center the data. This just means subtracting the mean face, which is the average pixel value across all the faces from the data, so that the dataset is centered around the origin. This way, we're focusing purely on the differences between faces. The goal of PCA is to find all the principal components, each of which is a linear combination of the feature column vectors. The optimization problem is to maximize the variance in the principal component subject to a constraint on the loadings. This is solved using eigen decomposition, which leads to an eigenvector problem with a covariance matrix. This matrix essentially tells us how each pixel varies with every other pixel. High values mean that those pixels tend to brighten or darken together. The eigenvalues tell us how much variance is captured in each direction. The eigenvectors are sorted by the size of their eigenvalues, and only the eigenvectors with the highest eigenvalues are kept. And the solution of the eigenvector problem is a principal component vector. This process is repeated for each principal component, ensuring each one has a covariance of 0 with each other principal component. The first principal component is the direction of maximum variance, and the next principal component has the next largest variance. Since the covariance between these components is 0, the directions of the principal component vectors are orthogonal. This process reduces our 10,000 dimensional data to something much more manageable, like 50 or 100 dimensions. Now we can project any face vector into this smaller space, reconstruct it, and even compare it to other faces, all while preserving the most important structure in the data.
Now here's where it gets really cool. When we apply PCA to face images, the principal components we get, the directions of maximum variance, can actually be reshaped back into images, and they look kind of like blurry, ghostly faces. These are called eigenfaces. The images you're seeing on screen are real eigenfaces. Each one represents a pattern that frequently appears across many different faces, like eyeshadows, cheekbone structure, or jawline curves. And here's the key idea: any face, including our instructor Prakash, can be represented as a weighted combination of these eigenfaces. Let's go back to our original image of instructor Prakash. The image of our instructor can be thought of as the average face from our data set. Basically, what you'd get if you averaged every face pixel by pixel. The images on the right, these are the most important deviations from that average. They're the top eigenfaces, the core ingredients that make each face unique. For example, if one of the eigenfaces emphasizes shadowing around the eyes and instructor Prakash had more of that than the average, his face will have a higher weightage on that eigenface. Mathematically, we can say that his face is a linear combination of these eigenfaces. So why is this useful? Well, instead of comparing every pixel of a face, which would mean comparing 10,000 numbers, we just compare the weights of each eigenface. So if two faces have similar eigenface weights, they're probably the same person, or at least very similar. That's how early facial recognition systems worked. Reduce a face to a few key components and compare those instead of the whole image. All you need is around 100 to 150 eigenfaces to represent almost all faces. And that's PCA's superpower: data compression without losing meaning.
Beyond compressing instructor Harish's face, PCA is used to simplify gene data, reduce noise in images, and even visualize high-dimensional stock data.
So the next time your phone unlocks with your face or you're staring at way too many variables, remember, it's not about having all the data. It's about knowing where to look in Harish's eyes.